All right, so we're going to talk about limits at infinity. So here we go. Let's do some limits at infinity, which is also called end behavior. So first off, I'm going to talk about two different things here, but we're going to start off with something that you talked about in pre-calculus, rational functions. And so this is actually a review lesson from pre-calculus on figuring out the limits going to infinity. Here, we'll put a little plus minus here. Limits going to infinity or end behavior using rational functions. So there's three rational functions, by the way, are functions where you get a polynomial divided by another polynomial, right? So let's just go over a few of them. We're going to first do the limit as x approaches infinity of, let's say, 5x squared minus 2x plus 4 over 15x squared minus 7x plus 12. And, well, basically what happens is we're going off to infinity. So let's plug in a tiny number. If I plug in 1, notice the top is going to be 5 minus 2 plus 4. But if I plug in 10, it's going to be 500 minus 20 plus 4. And if I plug in 100, it's actually going to be 5,000 minus 200 plus 4. So we notice as we keep increasing the value of x, the plus 4 doesn't change in value, and so pretty much it's going to become less and less significant as you go to infinity. So you can ignore the 4, but you can actually even ignore the 2x, because basically, I mean, if I went to 100 and this is 50,000, then and this is only 200, 50,000 minus 200 is not a big deal. And so you can kind of imagine that's only plugging in 100. If I went and plugged in 1,000 or maybe 10,000 or something like that, this term actually becomes less and less significant. So when you're going off to infinity and you're dealing with a rational function, you actually only have to look at your leading term. So your leading term here is an x squared. All the other ones don't really matter. We can ignore, and then we realize, well, 5x squared and 15x squared, they just cancel and reduce, and really we are left with 1/3. So this thing is going to approach 1/3 as we go off to infinity. And as you go to, so what is this called? This is going to be a horizontal asymptote. Right, so it's called a horizontal asymptote at y equals 1/3. So let's keep going now. All right, so that's pretty easy. This is true when you have a degree that is equal both on the numerator and the denominator. So let's do a different one. Let's do maybe the limit as x goes to negative infinity of, let's do 7x cubed plus 4x minus 12 over 5x squared minus 2. Well, basically what happens here is as we plug in larger and larger numbers, negative 1,000, negative, things like that, this term is going to grow the fastest. On the bottom, it's going to be this term. But we notice that this term won't grow nearly as fast as the numerator. And so since the numerator is going to grow much, much more quickly, this thing's going to go to a very large number, and this thing is going to go to a smaller one. Now, when you take a very large number and divide it by a small number, you're actually just going to come up with a large number. So this thing is going to approach a fairly large number. Now let's figure out if it's a negative or positive, though. Well, if I'm going to negative infinity, then this term right here will be negative. So this is going to be a very large negative number, while this term, since it's squared, is going to be a positive number. So this thing will actually end up going to negative infinity. By the way, this is called a slant asymptote. If I wanted to do the exact same thing, but this time going to positive infinity, basically both the top and the bottom is going to be positive, and so it's going to go to infinity. The idea of a slant asymptote is basically, weird things can happen in here. Maybe you've got, in the middle, but basically what happens is you're going to have a dashed line that has a slope of 7/5. Because if you were to reduce this, just the first two terms, when you reduce this, what do you come up with? You come up with y equals 7/5 x, where the x comes from the top, right? And so this is basically the equation that that this function will actually approach if you take it off to infinity. And so that's the line of 7/5 x, and it's going to approach that. And it'll approach it such as, maybe, who knows, maybe you even have like a vertical asymptote here, and maybe you have another one, and maybe you have like things like that. Who knows? Whatever happens in the middle could happen in the middle. Weird things. And then, but as we come out here, it's going to approach. That's the key. It's going to approach this dotted line as it goes off to infinity. And it'll approach this dotted line as well as it goes off to negative infinity. So it's going to approach those two lines, that dotted line, as it goes off to the right and to the left, sending it to negative infinity and infinity respectively. Great. All right. Last one is going to be, what if the limit as x approaches infinity is of a rational function where the 6x minus 4 and 3x squared plus 5. So the larger power is on the bottom. Well, again, you can ignore, then reduce. So in reality, we're asking for the limit as x approaches infinity of, well, it looks like 2 over x, right? But 2 over x, if I go to infinity, is just 0. So the answer here is going to be 0. And that's actually the exact same thing if I went to negative infinity, because if we go to negative infinity and we're dealing with 2 over negative x, yes, you're talking about approaching 0 from the negative side instead of approaching 0 from the positive side, which is up here, but you're still approaching 0, and so the answer is, in fact, 0. Okay, let me throw a little slightly tricky one at you, so you have to think a little bit. We're going to do the limit as x approaches negative infinity of 3x cubed minus 5x over the square root of 9x to the 6th plus 7. Okay, so again, the constant doesn't really matter. The lower terms don't really matter, so we can ignore those two. And so really we have this. But again, so we'll rewrite it as the limit as x approaches negative infinity of 3x cubed over the square root of 9x to the 6th. Now, what happens to the square root of 9x to the 6th? If I plug in a negative number, taking it to the power of 6 means that it's going to actually be positive. Then we're going to take the square root, and the square root of a positive number is positive. So, although this thing actually reduces to the limit as x approaches negative infinity of 3x cubed over 3x cubed, we realize that no matter what we plug in here, this has to be positive. So you can put it in an absolute value. Something divided by itself is always just simply 1. So this thing is going to go to 1. But since we're going to negative infinity, this thing is actually going to equal negative 1. Because the top will be negative, but the bottom will always be positive, so it'll be negative 1. But if I did the limit as x approaches infinity of the exact same equation, we can just kind of follow it along and realize, okay, if I'm going to positive infinity, this thing is positive, this thing is positive, they're the exact same. This thing would actually go to 1. So we'd actually have two separate horizontal asymptotes. One, as we go to the left, will be negative, and the other, as we go to the right, would be positive 1. That's kind of an interesting thing. But so just be careful of that. Be careful, kind of run through your mind, okay, what happens when I plug in a negative? What happens when I plug in a positive? Is this whole thing going to be negative, or is the whole thing going to be positive? You do have to kind of check that out. So that's good. All right. The other thing I want to mention is something called a oops, there is no H in sandwich. Let's redo that. All right, let's try that again. I'm very bad at spelling, by the way. So, sandwich theorem, also known as squeeze theorem. Okay, so basically, the squeeze theorem or sandwich theorem states that if g of x is always less than f of x, which is always less than g of x, f of x, which is always less than, let's go with h of x, okay? For all x. Upside down A means for all, by the way. So if this is true, and the limit as x approaches A for g of x equals the limit as x approaches A for h of x, which let's say it equals some number, we'll call it L, then the limit as x approaches A of f of x also must equal L. Graphically, what does this mean? This means that, okay, let's say here's A. Let's say this right here is, this would be g of x. Let's say right here is h of x, and we know that f, although we don't know what it does in the middle, we know that it resides in the middle. So this one's f of x. Well, if we know that g of x limits out to L, and we know that h of x limits out to L, and f has to be in the middle of those two, then it must also limit out to L, right? So basically, if you can squeeze it in between. Now, where does this actually matter? Okay, I'm just going to give you one example, but it's going to be a pretty easy one. And it's also going to look like every other possibility. So, all right, here we go. The limit as x approaches, we'll do infinity, of 1 minus the cosine of x over x squared. All right, well, what do we know? Well, I do know that cosine of x jumps from positive to negative, positive 1 to negative 1, right? So what I actually know is that, well, at the most, cosine could possibly be 1. So 1 minus cosine of x over x squared must always be, well, this could be as small as 1 minus 1, which is 0. So basically, always has to be greater than 0 over x squared, right? Which 0 over x squared actually just equals 0. So we know that this must be greater than 0, or 0 is always less than this function. We also know that this function must be less than, well, what if this thing was negative 1? 1 minus negative 1 is 2. So it's got to be less than that. And so we know this fact, which, by the way, harkens back to this fact. We know that our function is in between two other functions. Now, let's do the limits of them. Well, the limit as x approaches infinity of 0 equals 0, and the limit as x approaches infinity, right, of 2 over x squared is also 0. And so the limit as x approaches infinity of 1 minus the cosine of x over x squared must also be, you guessed it, 0. And that's the squeeze theorem in action. All right, so that's limits that go off to infinity as x approaches infinity and negative infinity. I'm going to give you a homework assignment on that as well, but I'll post this video in a second. So I will, yeah, anyway, hope you enjoy it.